Okay, so this is the second part of the standard level atomic structure section, and we need to look at electron configuration. So here are what you'll hopefully understand by the time we finish up. You can have a read through these yourself, so we'll come back to them at the end to check that you have got them all. But what we're dealing with today, a very big part of what we're dealing with today, are these emission spectra, and we touched on them in the last presentation, but you hopefully have seen when you do the experimental work in the labs these gas discharge tubes. And so what we've got is our noble gases, and they're having a large amount of electricity put through them, and you can see they're giving out some very pretty colours. And we can explain what's going on when we think about what the electrons are doing. And this phenomenon shows us that the electrons are existing in energy levels or shells. And so if we take an electron and if we heat up the atom, or we give it electricity, so we give it some energy, what we find is that the atom can go up to a higher energy level. Okay, so it gets further away from the nucleus. It's got a bit of energy, goes up to a higher energy. Eventually, that's going to have to drop back down again. And when it drops back down, the energy that it absorbed on the way up, it re-emits it. And it emits it in the form of a photon or some light. Okay, so call it HV, but light coming off. And sometimes that light will be in the visible region of the spectrum, and as a result we see a colour, and you saw that very nicely with these materials here. So this is our electromagnetic spectrum, and this section here, the visible region, you can see we've got red, orange, yellow, green, blue, indigo, violet. Other side we've got infrared past the red, and below the violet we've got ultraviolet. And you can have a look around at this yourself, but you can see as we move through the electromagnetic spectrum, this is going to correspond to a high frequency. So at this end, you can see we've got many wave fronts together. This is a high frequency, this is a lower frequency, and at our high frequency that also corresponds to a short wavelength. Whereas down here we've got a long wavelength. I think in higher level we'll spend some time looking at some calculations that relate the speed of light, the speed of the electromagnetic radiation, to the frequency and the wavelength. And of course this is fixed for dealing with light, 3 times 10 to the 8 meters per second. These are different subsections of it. We talked about frequency, we talked about wavelength, and you can see the position of the visible region. So where are we going to see these colours? Well, we can get that entire spectrum of visible light if we shine a light through a prism. So the white light goes in, the prism breaks it up, and you can see that every single colour is present. There's no gaps. That's what constitutes a continuous spectrum. If you compare that with a emission spectrum, you can see we do have gaps, right? And we have only certain energies present, certain colours are visible. And so when we heat something up, we're going to start to see an emission spectrum. And it comes down to these discrete transitions between the energy levels, that only certain things can be allowed. Down here, the opposite, the inverse if you like. So we're emitting some light, we're letting those bits be absorbed, what's left is what we're seeing, and we've got an absorption spectrum. But from the point of view of your course, the important ones are continuous spectrum and emission spectrum. We need to understand the difference. So all wavelengths present here, and only discrete wavelengths are here, and we've got gaps. So if we think about what was happening here, we've got these energy levels, 1, 2, 3 energy levels there. If we kind of flatten that out, we can look at energy levels like this as well. So this is our first energy level. We've got n equals 1 closest to the nucleus. Then further away from the nucleus, our number of our energy level, or our principal quantum number, so it's called, increases. So further away from the nucleus, notice as well that these lines are getting closer and closer and closer. And eventually, these lines begin to converge. They get so close together that there's no difference between them. And where they finally meet, where there's no difference between the energy levels, we can say the electron's been ionized. It's been lost. Right. So we've excited our electron up. It's up in one of these higher energy levels, and it drops back down. So remember, we're dealing just with hydrogen, so we've only got one electron to worry about. So if our electron goes up and it falls all the way down back to the first energy level, we've got quite a large difference in energy there, and it re-emits that. Now because it's a big step down, it's a large amount of energy, the radiation that's coming out of that is in the ultraviolet region. Over here, if we fall down just as far as the third energy level, smaller distance, the energy that's being emitted there corresponds to light that falls in the infrared region. But what's maybe most of interest is if we fall down to the second energy level and get a series of lines to do with that, you can see it's in the visible region. So this would give us colours that we would see. Sure enough, you could see these transitions happening here. So you've probably got a little bit of an understanding of electron configurations, and you've been taught maybe in the past, okay, the first shell, the first energy level, my n equals 1 can hold 2 electrons. My second energy level, n equals 2 can hold 8, and the third one can hold 8. And that's fine. It all works very well up to about calcium. It works well with ions as well. But if we go beyond calcium, if we think of trying to do that with iodine, we have a bit of a problem. Right, and if again, we do still rely on this a bit, particularly for those first elements. If I'm thinking of sodium, sodium's in group 1, it's got 1 outer electron. Oxygen's in group 6, it's got 6 outer electrons. Aluminium's in group 3, it's got 3 electrons in its outer shell. So it's still quite useful to be able to do that quickly. But if we want to go beyond calcium, we need to come up with a more advanced system. And we're going to have to bring in some new rules. So there's 3 rules that we're going to make use of. The Aufbau principle. So an electron will go into the lowest energy orbital available. So in other words, the one closest to the nucleus. So we're going to fill up n equals 1 before we would fill up n equals 2. That's the case. The Pauli exclusion principle. No more than 2 electrons can occupy an orbital. We'll see what the word orbital means in a moment. And then finally, Hund's rule. An electron will occupy an orbital singly before pairing up. And again, we'll look at some diagrams that will help us explain what that means. So, let's look at these terms. First term we saw there was energy level. So this is our principal quantum number, the n if you like. And we saw it in the hydrogen spectrum. There we go, n equals 1, n equals 2, n equals 3, n equals 4. So these are the energy levels. And as a little aside, for the first few energy levels at least, if you write in the energy level number into this equation, so if it's 1, it tells you how many electrons can go into that energy level. So for our first energy level, it can hold 2 electrons. Our second energy level can hold 2 times 2 squared, which is 8 electrons. Our third energy level can hold 2 times 3 squared, which is 18 electrons. It's a useful little rule of thumb. So within those energy levels, we also have sub-levels. So my n equals 2 second energy level actually consists of S and P sub-levels. My third energy level contains S, P's and D's. And my fourth level will contain S, P's, D's and F's. So they're different sub-levels. Now those sub-levels are further split up into what they contain, and they contain orbitals. Now, there's two shapes of orbitals that you need to be familiar with, and that's our s and p orbital. So if this is our s sublevel, it just contains one s orbital, and that s orbital can hold 2 electrons. So if you're asked for the shape of an s orbital, it is spherical. The p sublevel actually contains 3 p orbitals, and so there's px, py, pz, px, py, pz. These are right angles to each other. Again, each of these can hold 2 electrons. So there's 2 electrons in here, up to 2 electrons in here, and up to 2 electrons in here. So our p's can hold up to 6. So an s sublevel can hold 2. A p has 3 orbitals, and because each orbital can hold 2 electrons, I can get 6 in my p shell. D, there are 5 orbitals, so I can get 10 in there. And with my F, there are 7 orbitals, so I can fit 14 in there. And if we look at these numbers, maybe not the clearest, but I've got 2 to do with my S, I've got 6 to do with my P, I've got 10 to do with my D, and I've got 14 to do with my F. It's no coincidence that if you look at the periodic table, you've got what would be described as the S block, which contains 2 columns. Then you've got your D block, which contains 10. Then over here you've got a P block, which contains 6. And then underneath you've got an F block that has 14 in it. So you can see that the periodic table has been set up as these sublevels and orbitals are being filled up. But let's have a look at how we fill these up, because remember the Aufbau principle says that we have to start from the energy lowest to the nucleus. Now, something that's useful is to be able to reproduce this diagram, because it shows you the order in which the electrons fill these orbitals and sublevels. So let's say we're dealing with magnesium, which has 12 electrons that need to go in. So the first thing we're going to do is we're going to fill up the 1s, and we said that the s orbital can hold 2 electrons. The next one along, the next highest energy, is my 2s, that can also hold 2. Then my 2p, that's going to take 6. Then my 3s, and that's going to be able to take 2. And together, that makes the 12 that completes magnesium. Sure enough, if you look at its position in the periodic table, I think more on this in the periodicity section, but you can see that it's the 3rd period, and it's the 2nd column. It's in the right hand side of the S block. Do the same with chlorine. We're going to go 1s2, 2s2, 2p6, 3s2, 3p, 5, 10, 17, there we go. So that's the electron configuration of chlorine. Selenium, again, same idea, start filling them up, follow the arrows, start building it up like this. 3p6, where are we down to? 4s2, 3d10, and we're going to have a 4p, so this is 10, 20, 30, 4 in there. It should be the 4th one along in the P block. Again, as a check, have I got the right finish? So 4 along in that P block. Then vanadium, do this as another example. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 10, 23. And you can also do the same thing for ions. So like you've got I minus here, it's going to be a bit longer. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 6, what are we up to? 10, 20, 30, 6, blimey. 5s2, 4d10, 5b6, 10, 20, 30, and remembering that because we're on I minus, we've got an additional electron. Okay, an additional electron, so you can see that we finished our p orbital with that extra electron going in. Okay, so that was a bit long-winded writing out that last one, and we can actually condense it down a little bit if we think about closed shells, because in chemistry it's only really the outer electrons that are going to be doing the chemistry for us. And so rather than writing out all this stuff which doesn't do anything, I can just list it as a noble gas configuration. So if we look at the example here of bromine, that is argon. It's not going to do any chemistry for us, so I'm just going to call it argon, and I've got my outer energy levels there. The other thing to look at is another representation called electrons in boxes. And here's an example of nitrogen. So nitrogen's 1s2, 2s2, 2p3, because it's 7 electrons that we have to put in. So we can show these electrons sitting in boxes. And if we remember the rules that we looked at back here, we're filling them up from lowest energy to highest energy. We're making sure we only put 2 electrons in an orbital. But if we then look at Hund's rule, it says an electron will occupy an orbital singly before pairing up. And so as we build up our electrons in boxes diagram, you can see that these are single rather than 2 in here and just 1 in here. And it's because we've got some repulsion. The electrons would rather have their own space rather than be close to each other in this orbital. So we get these singly set up electrons. Right, a couple of things to be careful of when we're dealing with transition metals. We always fill up the 4s before we fill up the 3d, which is what you'd expect from our chart. But then when we come to ionize, when we remove electrons, we actually end up removing the 4s first. Okay, so if you're working with transition metals, D block elements, you need to remove the 4s when you start writing down the ion structure. The 4s electrons will go first. And then finally, one last thing to keep in mind as well is if we're dealing with chromium or copper, these are the only 2 examples you need to worry about, chromium and copper. Rather than being, in the case of chromium, 4s2 3d4, because the 4s and 3d shells are quite close in energy, we find that one of these s electrons hops across to the 3d, and we have a half-filled shell here, and it gives it a little bit of extra stability. Same with copper, rather than being 4s2 3d9, it exists as 4s1 3d10. Just 2 standalone anomalies, if you like, to keep in mind when you've been asked about an electron configuration. If it's chromium or copper, just be careful to remember that these small changes happen. Okay, so this is what I'm hoping you've picked up from the session. I hope that was of use.